Size and composition. The Sun is a nearly perfect sphere of hot plasma, heated to incandescence by nuclear fusion reactions in its core. With a diameter of approximately 1.39 million kilometers, 864,000 miles, the Sun is about 109 times wider than Earth, and its mass is about 330,000 times that of Earth, accounting for about 99.86% of the total mass of the solar system. The Sun's composition is about 70% hydrogen and 28% helium by mass, with trace amounts of heavier elements, including oxygen, carbon, neon, and iron. The Sun's interior is divided into several layers. The core is the central region where nuclear fusion occurs, generating energy through the conversion of hydrogen into helium. Above the core lies the radiative zone, where energy is transferred outward by radiation. Beyond that is the convective zone, where energy is transferred by the movement of hot plasma. The visible surface of the Sun, known as the photosphere, is the layer above which light escapes into space. Above the photosphere lie the chromosphere and the corona, which are visible during solar eclipses. The Sun's enormous size and mass make it the dominant body in the solar system. Its gravitational pull keeps the planets in their orbits and influences the behavior of comets and asteroids. The Sun's energy output, known as solar luminosity, is approximately 3.8x 10^26 watts, which is produced by the fusion of hydrogen into helium in its core. This energy is released in the form of electromagnetic radiation, including visible light, ultraviolet radiation, and X-rays, nuclear fusion, and energy production. The Sun is a main sequence star and thus generates its energy by nuclear fusion of hydrogen nuclei into helium. In its core, the temperature is about 15.7 million Kelvin, and the pressure is roughly 250 billion atmospheres. This extreme environment allows nuclear fusion to occur, releasing an enormous amount of energy. The fusion process involves several steps, collectively known as the proton-proton chain reaction. The first step in the proton-proton chain reaction is the fusion of two protons, hydrogen nuclei, to form a deuteron, releasing a positron and a neutrino. The deuteron then fuses with another proton to form a helium-3 nucleus, releasing a gamma ray. Two helium-3 nuclei can then fuse to form a helium-4 nucleus, releasing two protons. Alternatively, a helium-3 nucleus can fuse with a helium-4 nucleus to form beryllium-7, which can then capture an electron to form lithium-7, releasing a neutrino. The lithium-7 nucleus can then fuse with a proton to form two helium-4 nuclei. The energy released by these fusion reactions is initially in the form of gamma rays, which are gradually absorbed and re-emitted by the surrounding plasma, eventually reaching the Sun's surface and escaping into space as visible light and other forms of electromagnetic radiation. The energy generated by nuclear fusion in the Sun's core takes about 1 million years to reach the surface, as it is continually absorbed and re-emitted by the dense plasma. The Sun converts about 4.26 million metric tons of matter into energy every second, producing approximately 3.8x 10^26 watts of power. However, the Sun's energy output is not constant. It varies over time due to solar activity, such as sunspots and solar flares. These variations can have significant effects on Earth's climate and space weather. Solar activity and magnetic field. The Sun is not a static body. It exhibits various forms of solar activity, which are driven by its magnetic field. The Sun's magnetic field is generated by the motion of conductive plasma within its interior, a process known as the solar dynamo. This magnetic field gives rise to various solar phenomena, such as sunspots, solar flares, and coronal mass ejections, CMEs. Sunspots are temporary regions on the Sun's surface that appear darker than their surroundings due to their lower temperature. They are caused by intense magnetic activity, which inhibits convection and reduces the surface temperature. Sunspots usually occur in pairs or groups, with each pair consisting of a leader spot and a follower spot. The number of sunspots varies over an 11-year solar cycle, with the number of sunspots peaking at solar maximum and decreasing to a minimum at solar minimum. Solar flares are sudden, intense bursts of radiation that occur when magnetic energy is released in the sun's atmosphere. They are often associated with sunspots and can release enormous amounts of energy in the form of electromagnetic radiation, including visible light, ultraviolet radiation, and X-rays. Solar flares can also accelerate particles to high energies in producing solar energetic particle (SEP) events. These events can have significant effects on Earth's upper atmosphere and space weather. Coronal mass ejections, CMEs, are large-scale eruptions of plasma and magnetic field from the sun's corona. They can release billions of tons of coronal material into interplanetary space at speeds of up to several thousand kilometers per second. CMEs are often associated with solar flares and can have significant impacts on Earth's magnetosphere, causing geomagnetic storms and auroras. The sun's magnetic field also gives rise to the solar wind, a stream of charged particles that flows outward from the sun's upper atmosphere. The solar wind carries the sun's magnetic field outward, creating the heliosphere, a vast region of space dominated by the sun's influence. The solar wind interacts with Earth's magnetic field, giving rise to the aurora and other space weather phenomena. Solar cycle and climate influence. The sun's activity varies over an 11-year solar cycle, during which the number and size of sunspots, solar flares, and CMEs wax and wane. The solar cycle is driven by the sun's magnetic dynamo, which generates a large-scale magnetic field that oscillates over time. At solar minimum, the sun's magnetic field is weak and dipolar, with a well-defined axis of symmetry. As the solar cycle progresses, the magnetic field becomes stronger and more complex, reaching a peak at solar maximum. The solar cycle has significant effects on Earth's climate and space weather. During solar maximum, the increased number of sunspots and solar flares can lead to enhanced ultraviolet radiation, which can heat Earth's upper atmosphere and cause it to expand. This expansion can increase drag on satellites and cause them to deorbit more quickly. Additionally, the increased solar activity can lead to more frequent and intense geomagnetic storms, which can disrupt power grids, communication systems, and satellite operations. The solar cycle also has long-term effects on Earth's climate. Periods of low solar activity, such as the Maunder minimum in the 17th century, have been correlated with cooler global temperatures, while periods of high solar activity have been correlated with warmer temperatures. However, the exact mechanism by which solar activity influences Earth's climate is still an active area of research. In addition to the 11-year solar cycle, the sun's activity also exhibits longer-term variations, such as the Gleisberg cycle, which has a period of about 80–90 years, and the Suez cycle, which has a period of about 200 to 210 years. These long-term variations may also have effects on Earth's climate, but their influence is less well understood than that of the 11-year solar cycle, heliosphere, and solar wind. The sun's influence extends far beyond its visible surface, creating a vast region of space known as the heliosphere. The heliosphere is defined by the solar wind, a stream of charged particles that flows outward from the sun's upper atmosphere. The solar wind carries the sun's magnetic field outward, creating a complex magnetic environment that interacts with the interstellar medium. The solar wind is composed primarily of protons and electrons, with trace amounts of heavier ions, such as helium, oxygen, and iron. It flows outward from the sun at speeds of about 400 kilometers per second, near Earth's orbit, but its speed and density vary with solar activity and latitude. The solar wind carries the sun's magnetic field outward, creating the interplanetary magnetic field, IMF, which spirals outward due to the sun's rotation. The heliosphere is divided into several regions, including the termination shock, the heliosheath, and the heliopause. The termination shock is the point where the solar wind slows down to subsonic speeds due to its interaction with the interstellar medium. Beyond the termination shock lies the heliosheath, a turbulent region where the solar wind and interstellar medium mix. The heliopause is the outer boundary of the heliosphere, where the solar wind's influence gives way to the interstellar medium. The heliosphere provides a protective barrier against galactic cosmic rays, high-energy particles that originate outside the solar system. The solar wind's magnetic field deflects many of these particles, preventing them from reaching the inner solar system and damaging spacecraft electronics. However, during periods of low solar activity, the heliosphere's protective effect is reduced, allowing more galactic cosmic rays to penetrate the inner solar system. Solar eclipses and transits. Solar eclipses occur when the moon passes between the sun and Earth, casting a shadow on Earth's surface. During a total solar eclipse, the moon completely covers the sun's photosphere, revealing the solar corona and allowing scientists to study its structure and dynamics. Total. Solar eclipses are relatively rare, occurring somewhere on Earth about once every 18 months. Solar eclipses have been observed and recorded by humans for thousands of years, and they have played an important role in the development of solar physics. During a total solar eclipse, the moon's shadow traces a path across Earth's surface, allowing observers within the path to see the sun's corona and any solar prominences or other features that may be present. The duration of totality, during which the sun's photosphere is completely covered, can last from a few seconds to several minutes, depending on the eclipse's geometry. In addition to solar eclipses, transits of Mercury and Venus also provide opportunities to study the sun and its atmosphere. A transit occurs when a planet passes directly between the sun and Earth, appearing as a small, dark disk moving across the sun's surface. Transits of Mercury occur about 13-14 times per century, while transits of Venus are much rarer, occurring in pairs separated by more than a century. Transits provide a unique opportunity to study the sun's atmosphere and the planet's atmosphere simultaneously. During a transit, the planet's atmosphere can be studied using spectroscopy, allowing scientists to determine its composition and structure. Additionally, the planet's passage across the sun's disk can reveal information about the sun's atmosphere, such as its temperature and density profile. Solar neutrinos and the solar neutrino problem. The sun produces vast numbers of neutrinos as a byproduct of nuclear fusion reactions in its core. These solar neutrinos stream outward from the sun and pass through space, providing a unique window into the sun's interior. Neutrinos are weakly interacting particles that rarely interact with matter, making them difficult to detect. However, their weak interactions also allow them to escape the sun's dense core unimpeded, carrying information about the conditions deep within the sun. The first detection of solar neutrinos was made by Raymond Davis Jr. and John N. Bacall in the 1960s using a large underground detector filled with cleaning fluid. This experiment, known as the Homestake experiment, detected neutrinos via the reaction 37Cl2O plus Ni, 37R plus Ed, which produced argon-37 atoms that could be extracted and counted. The results of the Homestake experiment revealed a discrepancy between the predicted and observed flux of solar neutrinos, a conundrum that became known as the solar neutrino problem. The solar neutrino problem persisted for decades, as subsequent experiments, such as Kamiokande and SAGE, also found a deficit of solar neutrinos compared to theoretical predictions. The resolution of the solar neutrino problem came with the discovery of neutrino oscillations, a phenomenon in which neutrinos change flavor as they propagate through space. This discovery explained the deficit of solar neutrinos, as the detectors were primarily sensitive to electron neutrinos, and in the other flavors, muon and tau neutrinos, were not being detected. The study of solar neutrinos has provided valuable insights into the sun's interior and the properties of neutrinos themselves. Neutrino oscillations have been confirmed by numerous experiments, and the parameters governing these oscillations have been measured with increasing precision. Additionally, the study of solar neutrinos has led to the development of new detection techniques, such as the use of heavy water and liquid scintillator detectors. Solar oscillations and helioseismology. The sun's surface is not static, It pulsates and oscillates due to the motion of plasma within its interior. These solar oscillations can be studied using a technique known as helioseismology, which allows scientists to probe the sun's internal structure and dynamics. Helioseismology is analogous to seismology on Earth, which uses earthquakes to study the planet's interior. Solar oscillations are driven by the motion of plasma within the sun's convective zone, which generates sound waves that propagate through the sun's interior. These sound waves cause the sun's surface to oscillate with a period of about 5 minutes, producing a characteristic pattern of velocity and intensity fluctuations. By analyzing these oscillations, scientists can infer the structure and dynamics of the sun's interior. Helioseismology has revealed a wealth of information about the sun's internal structure and dynamics. For example, it has shown that the sun's differential rotation, in which the equator rotates faster than the poles, persists throughout the convective zone and extends into the radiative zone below. Helioseismology has also revealed the presence of large-scale flows, such as meridional circulation and zonal flows, which play an important role in the sun's magnetic dynamo. One of the most important results of helioseismology has been the precise determination of the sun's internal sound speed profile. This profile can be compared to theoretical models of the sun's interior, allowing scientists to test and refine their understanding of stellar structure and evolution. Helioseismology has also provided insights into the sun's composition, particularly the abundance of helium in the convective zone. Solar irradiance and climate. The sun's energy output, known as solar irradiance, is a crucial factor in determining Earth's climate. Solar irradiance varies over time due to solar activity, such as sunspots and solar flares, as well as long-term changes in the sun's luminosity. Understanding the relationship between solar irradiance and climate is an active area of research, with important implications for predicting future climate change. The total solar irradiance, TSI, is the amount of solar radiation received at the top of Earth's atmosphere, measured in watts per square meter, WM2. The average TSI is about 1361 WM2, a value known as the solar constant. However, the TSI varies over time, both on short timescales, minutes to hours, due to solar activity, and on long timescales, years to centuries, due to changes in the sun's luminosity. Short-term variations in TSI are primarily due to solar activity, such as sunspots and solar flares. Sunspots, for example, can temporarily reduce the TSI by blocking a small fraction of the sun's light. Solar flares, on the other hand, can briefly increase the TSI by releasing large amounts of energy in the form of electromagnetic radiation. These short-term variations can have significant effects on Earth's upper atmosphere and space weather. Long-term variations in TSI are thought to be driven by changes in the sun's magnetic activity and luminosity. For example, the Maunder minimum, a period of low solar activity in the 17th century, coincided with a period of global cooling known as the Little Ice Age. Conversely, periods of high solar activity, such as the modern maximum in the 20th century E, have been correlated with global warming. However, the exact mechanism by which solar irradiance influences Earth's climate is still an active area of research. In addition to direct heating, solar irradiance can also influence Earth's climate through its effects on atmospheric chemistry and dynamics. For example, ultraviolet radiation from the sun can break down molecules in Earth's upper atmosphere, leading to the formation of ozone and other chemically active species. These species can, in turn, influence the atmospheric circulation and climate. Solar evolution and ultimate fate. The sun, like all stars, is constantly evolving as it consumes its nuclear fuel and ages. The sun is currently in its main sequence, phase 8, during which it generates energy by fusing hydrogen into helium in its core. However, this phase will not last forever. Eventually, the sun will exhaust its supply of hydrogen and enter the next stage of its evolution. As the sun ages, its core will become increasingly dense and hot, causing the outer layers to expand and cool. This expansion will turn the Sun into a red giant, a phase during which its radius will increase dramatically, potentially engulfing the inner planets, including Mercury, Venus, and possibly Earth. During the red giant phase, the Sun's luminosity will also increase significantly, leading to intense heating of the remaining planets and potentially rendering them uninhabitable. After the red giant phase, the Sun will enter the asymptotic giant branch, AGB phase, during which it will experience a series of helium shell flashes and thermal pulses. These events will cause the Sun to lose a significant fraction of its mass in the form of a stellar wind, creating a planetary nebula. The remaining core of the Sun will then contract and heat up, eventually becoming a white dwarf. White dwarfs are the final evolutionary stage for stars like the Sun, which are not massive enough to become neutron stars or black holes. A white dwarf is a compact, dense object with a mass similar to the Sun, but a radius comparable to Earth. White dwarfs cool slowly over time, eventually fading to become black dwarfs, although the universe is not yet old enough for any black dwarfs to have formed. The ultimate fate of the Sun is still billions of years in the future, but understanding its evolution is crucial for predicting the long-term habitability of the solar system and the eventual fate of life on Earth. Additionally, the study of the Sun's evolution provides insights into the life cycles of other stars and the formation and evolution of galaxies. In conclusion, the Sun is a complex and dynamic object, with a rich array of phenomena and processes that continue to captivate scientists and enthusiasts alike. From its vast size and energy output to its intricate magnetic field and solar activity, the Sun plays a crucial role in shaping the solar system and supporting life on Earth. As our understanding of the Sun continues to grow, so too does our appreciation for its beauty and complexity.